Hello, this is the 12th video for my linear algebra reading of the book by Axler. Okay, last time we ended with the concept of diagonalization of a linear operator, and then we have also covered the eigenspace, the space of eigenvectors, and then we consider how you get a how uh, we have a diagonalization of an operator and also of the matrix associated with a linear operator. So in the previous discussion, we have not considered the notion of length and angle in our space R2 and R3. And now in the chapter 6, this is chapter 6 of the module of the book. We have the title is Inner Product Spaces. And then the first section we will cover inner products and norms. And then yeah, let's continue. So first we recall and set some notations that it's just when we speak of our V here, let me state F first. F is our this is just either our complex or the real numbers, the set or the field of real numbers. And then here it is we have letter V for a vector space over our field F. Let us start. Inner products. So as a motivation, let us consider an xy plane here, and then we have some point given by x1 and x2, and then let us call this x. So here it is, we picture this as a picture of R2 or a caricature. And then if we have x here in R2 given by x1, x2 here, we have the notion of length. So we have the notion of length. In this case, we call this the norm of our x here. It's denoted, we denote this as x with 2 bars. And then this is just defined as follows. You get x1 squared plus the second component squared. In case it's R3, you just extend this to x3 squared, okay? And then let me generalize for x here in Rn, and then given by this, and your norm of x is just the square root of x1 squared plus up to xn squared. Okay. Okay, let us define some elementary definitions from our calculus. We get x and y in Rn, then dot product of x and y, denoted x dot y is given by x1 y1 plus 2 xn yn. Here our x here and y is given by the ordered n tuples. Then okay, so that's it. So we can think of vectors as points instead of arrows, and then x should be interpreted as a distance from the origin. So here, the dot product of a number in Rn, we just say that if we get, this is just our what? Our x dot with x. This is for all x in Rn. And recall the following properties of dot product. Number one, we get the dot product is always greater than or equal to 0 for all x Rn. And then number two, x dot x is just 0 if and only if this x is 0. And three, the for a fixed y in fixed y in Rn, you get this one gets this one. This is the dot product. Can think of this as a function. Takes an element here, it is mapped to the dot product of x and y. This is a linear map. And lastly, we have your xy is equal to y dot x. Here, this is for all x and y Rn. So these are properties of the familiar properties of that product in the n-tuples, ordered n-tuples, the set of ordered n-tuples. Now, we can, of course, we are in algebra, and this approach of learning abstract linear algebra is more on abstracting or in an abstract sense. So what we want to do is to generalize this notion of dot product, and we call we want to abstract this and then just state them as properties, and then make an abstraction out of this. So, but in R, we have a slightly because we are working with R and C, we can copy, we can have a corresponding notion for this in case our we are in the complex vector space. So we have these properties here, and we want to make an abstract structure with these properties such that we can make a definition that will be useful for both the real and the complex vector space. Here we are only concerned with the real vector space, but we want to make structure such that it's okay with the complex vector space. But before that, let me recall some definitions from complex numbers that you have before. So suppose that we have a complex number a plus bi in C. Now, of course, a and b here are real numbers. We denote the absolute value this of our a lambda is just a squared plus b squared. And then for the conjugate, this is called the conjugate of our lambda. So we just take lambda bar is just a minus b. So here, this is replaced with negative sign. Okay. And third, we get lambda squared is just lambda times the conjugate of lambda. All right. So also, this is from basic complex analysis that we get C for Z. This is just square root of the magnitude of Z1 squared up to the magnitude of Zn squared. Here, Z is in the n tuples of complex numbers. So for all, this is in the setting of complex numbers. And also, we have Z here squared is just equal to Z1 bar plus up to Zn bar from this notion here. Okay. So we want to think of the norm of Z squared as inner product of Z with itself, and as we did in Rn, and thus we we suggest that for an inner product of W in Cn with Z, we just write if we get W and Z in Cn, we get W1, Z1, and up to W and Z n bar. So this is just the inner product of W and Zn, where of course W is an ordered tuples W1 to Wn in C to the n. If the rows of W and Z are interchanged, the expression above would be replaced with its complex conjugate. In other words, we should expect that the inner product of W and Z equals the complex conjugate of the product of Z with W. And yeah, that's it. So for notation, let us fix some notations here. If here we have lambda and C, lambda greater than or equal to 0 means lambda is a real number, positive. And we UV here will denote inner product. And what? Some people UV, some texts use this. This is used by some text. Okay, let us now define inner product in the more general notion over F, wherein F can be R or C. An inner product on our vector space B over F is a function from which takes an ordered pair UV to UV. Here, UV is where UV is an element of V and UV here is an element of F and has the following properties. Number one, we get positivity. This means V and V greater than 0 for all V in our vector space V. Number two is definiteness. This is V is only equal to 0 if and only if your V is equal to 0. Number three, additivity in the first slot. This is how it looks. So if you have U plus V, and then we have W here, you can add, you can expand, you can have V. For the first slot, you can expand, you can sort of distribute it here course, for all V, W, and U in the vector space B. And then the fourth one is homogeneity in the first lot. Actually, we can prove later on homogeneity in the second slot and something like that. All right, this is how it looks. So lambda U V, you can factor out the lambda and then U V. Of course, this is for all U and V in the vector space and for all lambda in the field F. And lastly, we get the fifth property. We call this conjugate symmetry. This is how it's given. U V is just equal to the conjugate of V U. This is for all U and V in the vector space. So note that some physicists physics. How do you spell physics? Physicists prefer the second slot. But well, as most mathematicians prefer it to be in the first slot. Now, if you have real vector space, if every real number equals its conjugate, we can, if we're dealing with real vector space, the last condition above, we can dispense with complex conjugate and simply state that if over R, V U is just V U. Let us consider some examples of inner products. Euclidean product. I have given this before. You have W1 to Wn. Wait, this is ordered. And then with respect to the vector Z1 to Zn, this is just equal to Z W1 Z1 bar up to Wn Zn bar. And then let us call this A, this is our B. We can also define if we get C1 to Cn scalars, and then positive, and then define W1 to Wn, okay, comma Z1 to Zn as C1 W1 Z1 bar, and then up to Cn Wn Zn bar. And also, we have a slightly example from real analysis. And then you have V, vector space of continuous functions on -1 to 1. -1 to 1, you have F and G. Their inner product is given by their integral from 1 to 1 of our F multiplied with G of X. Okay, so I think you can verify that these are all inner product, it satisfies our above definitions. Okay. So for example, for letter A, um, this is 0 if and only if our z here is just 0. Here, the multiplication is multiplication over c on c. Here, then the addition is just addition in complex numbers, in complex vector space. Okay, let's continue. So now we defined an inner product. Now let us consider a space associated with inner product. So an inner product space is a vector space B with an inner product. And then the most important example here is f to the n, where the example here is f to the n with Euclidean inner product. And then this is our default inner product. If we are not given what we don't mention the inner product, by default you consider it to be the Euclidean inner product. Let us fix some notation. From now on, we consider our V here as a inner product over our field F. We're just changing our language here. So an inner product space is a vector space along with the inner product on that vector space. And when we say vector space is an inner product space, we're also thinking on an inner product on V that is lurking nearby, is obvious from the context. So let us consider some properties of inner product. Let's prove some of them and then leave some of them as exercise. Properties of inner products. So number one, for a fixed, this is abstraction of what we have earlier in R, in C to the N. For a fixed U in V, the function that takes V to our inner product, V U, is a linear one. And then the second one, if we have 0 U is equal to 0 for all U in V. Number three, we get U 0 is also 0 for all U in V. Number 4 is we get U and then V plus W. So this is like the in the second slot. What do you call this earlier? Additivity in the second slot. So this is just U then V plus U W. This is for all U, V, and W in our vector space V. And number 5, we get U here and then lambda V. Can put the lambda out too and then conjugate U, V. This is for all lambda in our F and for all our U and V in the vector space V. So let us prove the first statement. This is A follows from additivity on first slot. and homogeneity. Okay. So additivity in the first that simply says that we have the following, and then the other one, homogeneity, we get the following. This is for scalar multiplication, and then this is for the vector addition. So if u and v here is in ano, you get here u plus v is also in inside the space. So, yeah. Letter B. For letter B, so follows from our A. And then what's the result? And then linear maps map 0 to 0. And the fact that linear maps map 0, linear maps map 0 to 0. All right, for letter C, we get similar and then apply conjugate symmetry. Yeah, I just leave this for reading and verification. For letter D, oh no, I'm messing with the numbering. Let me call this 1, 2, 3, 4. For number 4, we get U, V. This is for all U, V, and W in the vector space, inner product space. You get the U plus U and then V plus W. This is just equal to the conjugate. And then we get U, wait, V plus W, and then the conjugate of the entire thing in U here. Now, we just copy the conjugate and then we apply the property earlier. This is just V and U plus V and W. Okay, so this is, again, we can take the conjugate term by term. V, W. And again, we get U, V plus W, V, which is what we want. Okay. And then for number 5, you have, we also used the property earlier. We have to invoke first the lambda V and then U here. We take lambda out and then V and U conjugate. And then the conjugate of lambda is just conjugate. And then the conjugate of this is just U and wait, I write it explicitly. So this is conjugate of this times conjugate of that. And then conjugate of lambda. Conjugate of this one is V and U. And this is what we want. So if you complete everything, so we have completed the proof. Now we introduce a new definition. Here V is a vector, an element of the inner product space. The norm of V given by V here is just the inner product of V with itself. Okay. Example. So the norm of, we get Z1 up to Zn here in F to the N, then the norm Z1 to Zn is just the square root of Z1 squared up to Zn squared. Why? Because It's just the inner product of using Euclidean inner products here. So Z1, and then with itself, we just have Z1, so Z1 squared, and that's it. Okay, let me pause a little bit. We have already encountered this earlier, but here we just state this in the language that we already developed. The other one is if you get here, F is in ano nga, C continuous on -1 to 1. This is a vector space of continuous on -1 to 1. The norm is given by the square root of, then we get to square this, and then with respect to x. And then after giving the norm, we have basic properties of norm. The first property is here for all v in our inner product space, the norm of v is equal to 0 if and only if v is 0. And letter b, the norm of lambda v is equal to the absolute value of lambda times the norm of v. This is for all lambda in our field F. Let me write this. Suppose V is a vector in an inner product space. The first one is easy. Second one is the following. The lambda of V squared is just lambda of V, lambda of V. So this is just lambda and then V, lambda of V. And again, we get lambda here and then lambda and then V, V. This is lambda squared, and then absolute value or the norm of V. Then if you take square roots of both sides, we get lambda V is just lambda times the norm of V. So that's it. Now we go to the concept of orthogonality. Orthogonal here, it's just a fancy word for perpendicular in the case of the vectors in R2. So U and V here are vector elements of inner product space, are orthogonal if your inner product of U and V is 0. And exercise, this is also already done in calculus. In R2, and then U and V in R2, check that U, V is just the norm of U times the norm of V times cosine of theta, where here theta is angle between our U and V in R2. course, U and V here, U is orthogonal to V if and only if your theta is 90 degrees. Okay. That means, or this cosine of theta is 0. Let me erase this first part. The cosine of theta is 0. And this means that U, okay, this is if and only if U is perpendicular to V. So in R2, just think of this as orthogonal is just perpendicular. Perpendicular. So it's just a fancy word of saying perpendicular. Now let us consider some of the results on orthogonality. First is 0 is orthogonal to all V in the vector space. And then 0 is the only vector in our V orthogonal itself. And these are easy to follow. So this is all of them are by definition. So here we get special case. No, my handwriting is not good with the stylus here. Pen. So V in R2. We can have a Pythagorean theorem. Okay. The next is a generalization of the Pythagorean theorem. So let us generalize the Pythagorean theorem in arbitrary inner product space. Suppose that you get U and V in the inner product space V, then your sum is just equal to this one and then V squared. So for the proof, this is just as easy expansion. So this is U plus V, U plus V. And then this is, for the first one, you get to distribute U plus U, V. And then you get plus V, U plus V, V. And then this cancels with this. So we get U, and then plus V, V, which is just the norm of U plus the norm of V squared, square of each term. And then that's it. That's the end of the. So now, suppose that U and V, suppose you have U and V in the vector space V, and then V here is non-zero. We can write U as scalar multiple of V. We can scalar multiple of V plus W, where W is perpendicular to V. Okay? Let me draw the picture here. The picture is you get the origin, then you get the vector V, and then you extend V up to here. So suppose this is V. This is C times V up to here. This is C times V up to here. And then we get a perpendicular vector W, and then this is our U. So U here, U is just the sum of this CV and this one by tail to tip to tail connection. So how do we write this one? So how to write our U as C times V plus this W. Notice that your U here is just what? And this W is just U minus CV. So we get is CV plus U minus CV. Okay. Now we need to choose C so that we want C here in F. So our V and U minus CV are orthogonal. That means this means that you get the inner product of U and of U minus CV and V be 0. That is, if we expand this, we get UV minus plus what? Negative CV and then V. So this is just UV here and then minus C. Then you get V. So this is just UV minus C, then V squared. And then our assumption is V here is not equal to 0. So we can divide. So how do we find C? So you get C here is just UV over the norm of our vector V. Thus, we can write U as follows. So you have UV over norm of vector V times V plus U minus the norm, the inner product of U and V over V squared times V. All right. So let me state this as a theorem. The derivation that we have earlier, let me formally state that as a claim. So suppose we get U and V in the inner product space V with V not equal to 0. If you set C be equal to the inner product of U and V over the norm of V squared, and we set W be U minus the inner product of U and V over V squared times V, then what we get? Then your U times V is W and V are orthogonal, and your U here is written as scalar multiple of V plus this W, wherein W here is an orthogonal vector to V. Okay, here, yeah. So the proof of this theorem is just what I said here, and then some sort of verification that U is a scalar multiple of V, and what? And plus the orthogonal vector V. Now, let's consider the next inequality. We have the Cauchy-Schwarz inequality. Cauchy, forgive my pronunciation. Schwarz inequality. All right, okay, sorry. So here U and V are also inner products base element. Then what can you say about the absolute value of the inner product of U and V is less than or equal to the norm of U times the norm of V. So let us quickly prove this. Okay. If V is 0, this is okay. Like very trivial. If V is not 0, then take U be equal to the following. You can do this because V is non-zero. And then here, U and W are orthogonal. So by Pythagorean theorem, the norm of U here is just equal to, you take the norm here of U, V. Of course, we have V here. This is a vector. This is a vector. And then this is a scalar. This part here is scalar times a vector. And this is a vector. This is again scalar. Okay. Plus W. So this norm, this is the norm here is just equal to U. So you can think of this as unit vector. So UV squared over base over V squared. Okay, wait. Let me think. Plus W squared here. So here we check that this P is gone. Okay. So because this is just this is somewhat normalized. You can check that. And then this is greater than or equal to this UV squared over V squared. And then if we multiply both sides, U squared and then V squared, just greater than or equal to the norm of U, norm of V squared. And then taking square root, you get U here, then you get V. This is U and V. Okay. Okay. Now, for the equality, when you're what? When this is when W is 0, and then this is left for you to check. That ends the proof. Sample of application of Cauchy-Schwarz is the following x1, y1 plus up to xn, yn is less than or equal to x1 squared plus xn squared, and then y1 squared up to yn squared. So for example, if we get two only x1, y1 plus x2, y2 is less than or equal to x1 squared plus x2 squared times x times y1 squared plus y2 squared, which is equal to x squared, tapos meron tayong y1 squared plus x1 squared. Then, okay, this is getting a bit long. Plus what? This one. X2 squared, y2 squared, oh, y1 plus x2 squared, y2 squared. In fact, they almost, they are equal in Rn. So, yeah. Now we proceed with the next result on inner product space. We call this the triangle inequality. So notice that all of the theorems here are somewhat, we get u, and then we get u plus v. This is our v. And then the triangle inequality says that the norm of u plus v is less than or equal to the norm of u plus the norm of our v. The proof here is, I will leave it again. This is just using, wait, let me do it here. So how do we do that? Get u plus v. You just have our u plus v, u plus v. And then this is equal to u plus v, v plus uv plus v, u. We have done this earlier, right? And then this is just um, u plus v, v plus u, v plus the norm and the conjugate of uv. So this part here becomes squared, and then this is v squared. And then here we get 2, the real part of u and v. And then we get here less than or equal to u squared plus v squared plus 2 times the magnitude of u and v. No, it's just magnitude. The absolute value of the magnitude of the inner product of u and v. Again, this is less than, greater than or equal to u squared plus v squared plus 2, and then u here, and then v here. And then this is equal to u squared plus v squared. So, yeah. This is for inequality. Quality follows when your u, the inner product on u and v, is equal to the u, the norm of u times the norm of v. And this happens when what? When u and v are ano, in the same direction. Or in other words, u is equal to c times v, and then c here is non-zero field element. I think I have left some for reading. And lastly, we will have this famous result from geometry. This is high school geometry. If you get the parallelogram, and then the parallelogram equality states that if you get the diagonals, the product, oh wait, the sum of the square of the lengths of the diagonal is equal to the sum of the square of the lengths of the four sides. So this is our u. This is our u. This is v. This is v. This is u plus v, and then this is u minus u minus v. Let me reverse the arrow. This is u minus v. So u minus v. So u and then v backwards. Okay. Here, this is the theorem says that if you get u and a v element of inner product space, then the result is you get the square of the diagonal, the square of each the sum. If you get the square of one diagonal, add to the square of the other diagonal, this is just equal to the square of each side. So the square of one side is u squared, and then the other side is v squared. And of course, we get two of them. And then the product here, the proof here is easy expansion. So you get u plus v, u plus v, plus u minus v, u minus v. So this is equal to u squared plus v squared plus u v plus v u, and then you get plus u squared plus v squared minus uv minus v u, and then these ones cancel. So what you get is just twice of u squared plus v squared, and this is the proof that we want. So I think we have a very as a quite theoretical approach here in inner product space. Now, I will leave it as an exercise to verify the examples like satisfy the necessary properties stated. Like, for example, you verify that here we get an inner product on that this function, this defined here is an inner product, this one, and also this one is an inner product. So maybe, yeah. Maybe I will end here. It's quite long recording already. So for the next meeting, let me write what's coming up next. So up next, we will have orthonormal basis. So what's an orthonormal basis? So orthonormal here is just or the list of vectors is orthonormal if it has norm 1 and is orthogonal to all the other vectors in the list. And of course, if this list is a basis, we get an orthonormal basis, but that will be the topic for next recording. And then after orthonormal basis, we will cover what we will have for orthonormal basis. We will stop up to wait, let me check. We will have we will also recall linear functionals on inner product spaces. And there are important theorems here, such as Square's theorem. This relates upper triangular matrix to some orthonormal basis. And also, we will have Square's theorem. These are important theorem. And then we have Rice representation theorem in the context of linear algebra and in the context of linear functional and inner product space. And I think we will cover this next meeting. So for now, let me end the recording here. So yeah, let me end the recording.